My name is Beddhu Morali. I'm a clinical associate professor in computer science. What I want to talk about is something called bounded linear computations. And, this morning we heard that there are not enough resources in Amazon Web Service, right, for doing certain operations. You also might have heard that GPT-4, which is coming out either this week or next week, it uses 100 trillion parameters. Okay, so that's what people say, right? 100 trillion parameters, if you use like 4 bytes per parameter, is 400 trillion bytes. Okay, so the amount of storage that you need, memory that you need, right, that is just for the parameters, right? Besides parameters, you're also going to have gradients. You have to have storage for the inputs and outputs and all kinds of other things. Okay. The issue is that, are there things we can do to reduce the number of parameters without compromising on the accuracy of your predictions, of your models? Okay. So that's the idea. So what I want to talk about is, what is a layer? Okay, so, there is a picture that shows 2 adjacent layers in generic layers. And if you see, let's say they are fully connected layers. So this equation up here, A is the activation function. And whatever is within the parentheses, that's the part that, is not bounded, okay? So the weights over here, right? So these weights are not bounded. Not bounded, I'll just explain what it means. And similarly, the biases are not bounded, okay? So let's, instead of very complicated equations, let's take a line, okay? So what we are interested in is, these are data points, okay? So if you see the trend is a positive slope, and suppose you start with a negative slope, okay? So you can solve this problem analytically, but let's assume we are iterating, okay? So we start with a line that is, has a negative slope. Obviously, it has to rotate, right? It has to rotate and match the positive slope. As it is rotating, right, you can, the slope, you can write it as tan theta, right? So this is the angle theta. So what happens when theta becomes 90 degrees, right? As theta becomes 90, your parameter m is going to shoot to either negative infinity or positive infinity, okay? So infinity is a valid value, right? As your line is trying to rotate, right? Your algorithm is doing the right thing, but your algorithm is not going to converge, right? So that is the problem, okay? So the manifestation of this unbounded linear operators expresses itself in the literature is called the vanishing gradient problem, okay? So what is the vanishing gradient problem? What they do is that, like I showed you the activation function a couple of slides ago. So these are a couple of activation functions here. If you see, for a value of -6, the gradient of this, right? This function is essentially horizontal here and horizontal here, okay? So which means if you take the derivative, it's going to be 0, right? So if your unbounded linear operator produces a value that is way out here, right? So then your gradient becomes 0. Gradient becoming 0 is not a problem, is not, okay. When you are trying to iterate, right? When you are trying to iterate, you do want to drive your gradients to 0, okay? That's how you converge. However, if your gradients go to 0 before you converge, then your model will not learn. Learning will stop, okay? All right, so people have developed many different techniques. If you trace the history of the advancement of AI, it is directly proportional to how we were able to solve the vanishing gradient problem. Okay, so one of the things people did was they came up with what's called regularization, right? You add terms to the loss function, L1 regularization, L2 regularization, okay? So what happens is when you add this, most of your weights are going to stay close to zero, but some of the weights that that grow will grow unbounded. Okay, so you cannot avoid the vanishing gradient problem just by using regularization. Okay, so the second idea that came is the ReLU, right? So instead of using sigmoid and tan-H activation, we use ReLU. Essentially, it's two piecewise linear functions. Okay, so on one side, it still has the vanishing gradient problem, but on the other side, it has non-zero gradient. Okay, and every layer will either produce zero or positive output, right? So that becomes the input for the next layer. So what happens if your input is always positive and your weight is negative? Okay, so some of the weights can dominate. Suppose a negative weight dominates, then the output from that layer will always be zero, right? Because anything, if the input is negative, the output is zero. Okay, so learning stops again. So when you traded ReLU for sigmoid, we introduced other problem that's called exploding gradient. Okay, so that's because we are allowing so as this thing keeps growing out, you're going to have sooner or later exploding values. Okay. All right, so the other approach people try, or it is there out there in the literature, is the so-called max norm regularization, right? So you set the max norm to be less than some C. In 2D, what does that mean? We are restricting tan theta, right? So when you're saying max norm is less than C, you are saying my tan theta cannot grow beyond a certain value, okay? Which means you are preventing your line from rotating, okay? Well, if you are in the wrong quadrant and you prevent your line from rotating, you are never going to get the right answer, right? Because your line is, your positive slope is the right answer. You are trying to prevent it from rotating. All right. So that's what I'm saying. What if the best fit is in the other quadrant? You're going to, have problems. However, what if this thing happens in higher dimensions, right? So you are preventing some coordinate from rotating. It is possible for gradient descent to find some other subspace and try to fit your data, okay? So there is another mitigate. Okay, so the one thing I forgot to mention is that when you go to ReLU, right, you have to double the number of parameters that you use for sigmoid, okay? Similarly, there is another idea called dropout, okay, that you see out here. It depends on a dropout ratio, which also increases in the number of parameters. If you use a dropout of 50%, you will double your number of parameters again, okay? So there is this idea called batch normalization. It was introduced in 2015 by a couple of people from Google. And essentially, the idea here is that they want to map all the weights, right? The products of weights times the input. They want to map it to a unit ball, right, in dimension. And then they introduce additional parameters, okay? So the alpha and gamma down here, those are the additional parameters they introduce that they need to learn, okay? So the idea of batch normalization is to, is to map these weights to unit balls. And when you introduce these additional parameters, then they are unbounded, okay? So there are, okay, I didn't intend it this way. All right. So if you compare max norm and batch normalization, the max norm only modifies the magnitude. It does not change the orientation. On the other hand, batch normalization, it projects everything to a unit ball, and it changes the orientation, and you have to have additional gradient computations becomes complicated. Okay. So there is this layer normalization. It is also very similar to batch normalization, and it also projects to a unit ball. But the orientation change is different compared to batch normalization. And so again, it has complicated gradients. Okay. Okay, so what happens is if you have unbounded growth in one weight, it would distribute that to other weights through the mean, right? So that's another issue. Okay. So what happens is that every one of these mitigation steps have introduced additional parameters. Okay, so when we talk about using, let's say, 100 trillion parameters, okay, so, all right. So what I did was, the linear part, I had a different formulation. So my formulation, what it does is it doesn't rotate, restrict, it doesn't restrict rotation like the max norm does. And it doesn't change orientation, or there is no unit ball projection, and there are no additional alphas and betas. Okay, my method has simpler gradients. And, when you project all these computations to a unit ball, you are essentially, losing information there. Okay, so we don't do those kinds of things. Okay. So she's telling me I'm out of time. So essentially, if you look at it, the market for machine learning is in 2022 is $21 billion, and 2029 is $209 billion. Okay, so those are all projections. So what we are going to do is we are looking for early investors and adopters, okay, of our method. And we are going to make more announcements soon.